This is May, June 2024, P4, ATP question. Starting with question number 1. It says that the student investigates the resistance. This is what he wants to do for the diode with the circuit shown below. We have a power source, we have an ammeter, we have a resistor P, and the diode connected this way. We can see that the diode is connected the right way around because the current leaves the positive terminal, flows through the ammeter, then if this junction was connected, then through the diode like this, and then back to the supply. So the orientation of the diode seems to be correct. But let's see what he wants to do with the junction XY. Say a student connects a voltmeter into the circuit to measure the potential difference across the diode. He's asking you to connect the voltmeter with its appropriate symbol across the diode. So let's remove these and let's try to connect a voltmeter over here. Since we're measuring the voltage of the diode only, we will be connecting the voltmeter in parallel with the correct symbol of the voltmeter like this, right? Okay. Next part, he says what the student is going to do. So he says that he connects the lead, connecting the terminal X and Y together. So X and Y are now connected completely like this. So the circuit completes. Closes the switch and then records the value of V and I with these respective ammeter and voltmeter. This will be your voltmeter and this is your ammeter. That's how we know these are the respective meters. And then opens the switch and removes the connecting lead. Okay, fine. So he says record readings in figure 1.2 in table 1.1. So let's go to table 1.1. This is table 1.1. Let's try to read the values by zooming in and seeing how we are going to read the values. This is the first time, probably in a very long time, that he is going to check whether you're able to read these values appropriately, properly or not. Now, notice that this is up to 1. So it is from 0 to 1, it is divided in 5 divisions. So 1, 2, 3, 4, and no, not like this. We're going to count it like this. So 1, 2, 3, 4, and 5. So 1 divided by 5 gives us 0.2, which means that each one of them is actually a value of 0.2. This is 0.4, this is 0.6, 0.8, and then 1.0 at this location. Similarly, 1.2, 1.4, 1.6, 1.8, and then 2.0. Since we don't need these, I've only written them down for your practice. Now we come down to this idea that this is basically greater than 0.8 at least, right? Now we can see that 0.2 is divided into 5 further divisions. If we look closely, we can see that these are actually 5 divisions. When you do that, this comes down to 0.04, right? So the first one will be 0.84. The second one will be 0.88. The third one will be 0.92, 0.96, and the last one will become 1.00, right? So that is how we're going to read this. But notice that this is actually somewhere in the middle of 0.8 and 0.0484, right? So what would this be? Since it's in the middle, it should be 0.82 at best, right? So when we are going to note this value down, notice that this is 0.82. So the examiner wanted you to accommodate this little possibility of the division or of the error you might have done because of the division. Then we move on to reading the ammeter's value, right? So let's zoom in. Again, we can see that there are approximately 10 divisions, right? So we can just straight away guess that this is going to be 0.1, this is 0.1, 0.2, 0.3, 0.4, 0.5, and so on up to 1.0, right? So this looks like that this is greater than 0.3, but less than 0.4. And since it's exactly in the middle, this looks like very easily 0.35. So that's why in the table we have mentioned 0.35, right? So we understand how to read these values. Then he says that calculate the value of R using these values. Now notice that this value comes out as, if you divide 0.82 with 0.35, this is your answer. That is going to be 2.3428. But we understand that the whole table of the resistant values is up to 2 significant figures or up to 1 decimal place. That's why we have to round it off or round this value off to just 2.3. Okay, we have to make sure that the values in the table have the same significant figures at least. The next question, he says, a student in part D, and he said record your answer, okay, to the appropriate number significant. And now he's asking you to take care of that ID as well. Then he says that another student connects a 3.3 ohm resistor, repeats the same experiment again, but with 2 different components. And the values of those components is mentioned in the table again, right? So resistance with the 6.8 and 10 ohms. He obtains the following values, respective columns, respective rows for those values. And he's asking you to use the same formula to recalculate these values to fill in the table. Now notice when you do that for this entry, when you use this formula, the answer is actually 0. If you zoom in, the answer is 0.2189189. But we've written this down as 0.22 because keeping in line with the rest of the table values, this is supposed to be, or this at least have to have the same outlook. Then we calculate for the second row of values and we get 4.263157895. You can do this by the calculator and you'll see you'll get this answer. So rounding it off to, again, 2 significant figures because we need to make sure that the rest of the table looks exactly the same. We need to make sure of that. Okay, so we have completed the table. Let's move on to the next. He says, as the resistance between X and Y is changed, the current in the circuit changes, as evident from the values as well. Examine the results in table 1.1. Describe the changes in current. Now, whatever is written in bold should be of your prime importance. Everything has to revolve around current, how it's being affected, right? So the voltage across the diode, has it changed when the current is changing? So let's go ahead and visualize that although the current is reducing, the value of I is decreasing as the value of R is increasing. But is there a significant change in the voltage across the diode? Maybe not. Maybe it's probably due to the errors of the instrument itself, but at least to our understanding, the values is not changing, or the values are not changing, or a negligible change between them. That's why we mentioned that there is a negligible change in resistance as current decreases. Sorry, the voltage. The negligible change in voltage as the current decreases. Again, what is happening? Describe how the resistance of the diode, right, affects the resistance of the diode. So is the resistance changing? So yes, the resistance of the diode appears to be increasing as the current appears to be decreasing. So that's what we've written down over here. Again, the simple observation from table 1.1 to check the ability of the student whether they can relate to the values or not, or they can figure out the trend or not. The resistance increases as the current decreases. Similarly, the student sets up the circuit in figure 1.1 again. The student finds that when the connecting lead connected across terminal X and Y, the switch is closed, the ammeter does not give a reading. He mentioned that the ammeter is fine, it's not broken, suggests the error the student might have made. So it's very likely that there are 2 possibilities the student or the second student who's conducting the experiment again might have done. So he may not have paid attention that the diode may have been mistakenly connected the other way around, right? Or if the diode was connected correctly, then it's possible that the power supply has been swapped. The terminals have been swapped by mistake, which will of course make the diode reverse biased and the diode will not be conducting any current so far or anymore. So there are 2 answers. You can choose any one of them. That the power supply is connected to the reverse terminals, the diode is connected incorrectly probably, and either the voltmeter is connected in series. You see, voltmeter has a very high resistance. It's almost infinite. And that's why you will find that across the components, voltmeters are connected in parallel, because we understand and we accept that the current through the voltmeter will be almost equal to 0, but just enough to give a reading, but overall it would be 0. So if you connect a voltmeter by mistake in series, since they have infinite resistance, there will be no current in the circuit according to V equals to IR, I equals to V over R. If you increase the resistance of the circuit infinitely high value, the current will go down to 0. So this is one of the problems that the student may have encountered or may have produced in the circuit. Okay. Question number 2, student investigates the rate of cooling, a very common question for ATP and under different conditions. Okay, this is the apparatus the student is using. He's labeling the apparatus as well. Then he mentions what he's doing. He pours 200 centimeter cube of cold water into a beaker this is not a beaker, this is a test tube. Okay, so the warm water probably will be inserted over here and the beaker will be on the outside. So this is the apparatus that you're using. The hot water is on the inside and the cool water is on the outside. Okay, fine. So pours hot water into the test tube until approximately 1/3 full. Lower the test tube, and then after 30 seconds interval, he is measuring the value of the temperature, right? Okay. He says the student measures the temperature theta of the hot water in the test tube. The thermometer reading is this as such. And we can see that the value at least is up to 1 degree centigrade, right? So this will be 70, 71, 72, 73. Okay. Then he says, record this value to the table. So we've done that, 73. But he also mentions that we need to complete the column headings by adding appropriate units and complete the time column. Now we can get to the time column secondly, but first we need to fill out the units. So time is in seconds, temperature in degree centigrade, again temperature degree centigrade. But how do we fill in the time table or the column? You see, in the procedure, he says that every reading has been taken by approximately after 30 seconds. So if the time starts from 0, then the consecutive readings will be after 30 seconds repeatedly, simultaneously, right? So 30, and then again after 30, then plus 30, plus 30, plus 30, and finally plus 30 until the end of the table. Okay. Describe one precaution that the student must take to make sure the temperature measurement is as accurate as possible. So the one common answer is avoiding parallax error, but just simply writing down avoid parallax error will not score you the marks. You need to mention how to do that. So keeping eye perpendicular to the scale or keeping the line of sight perpendicular to the scale to avoid parallax error will get you 1 mark. You identify how to do it, you identify how to correct it, and you identify what the problem is. So problem with the solution will get you the 1st mark. Okay. Again, thermometer should be submerged 1/3. These are all common answers. 1/3 submerged in the test tube. Thermometer should not be touching the sides or the base of the beaker so that it does not measure the temperature of the glass itself. We want to measure the temperature of the liquid. And keep the stopwatch close to the thermometer. Now, this is primarily to overcome the delay a person or a student might have while measuring the temperature and looking at the stopwatch. If they are far away from each other, then just the time spent in looking away from the thermometer, it's possible that you may lose 1 or 2 seconds. So we want to make sure that everything is as accurate as possible. So keep the thermometer and stopwatch in your line of sight, or at least very close to each other, so you can measure them collectively at the same time. Now he says that hot water is now replaced with, the cold water is replaced with the warm water, and the experiment is repeated. And the second values are mentioned in the second column. So warm water, and then one of them is with the cold water. And we can see the one that has the cold water, the temperature decreases very rapidly, and the final temperature is much lower than with the warm water, right? Primarily due to the thermal equilibrium difference and the heat gradient. He says one of the students' readings for the warm water recorded in table 2.1 is anomalous. Anomalous is related to the idea that it's possible that the reading was taken incorrectly. It's possible that the student misread the value, or due to an external bias, due to a bias of their own mind, that this is the value that should exist, but actually that value didn't come from the thermometer, right? So because there are many values that have to be taken down, it's possible that the experimentation causes a bias in the mind of the student. So he's asking you to identify where this value exists. So let's go for the warm water. We can see that the trend generally follows that the temperature is decreasing. Okay, fine, it's decreasing, and so on and so forth. But at this location, we can see that there is a problem, right? The trend calls for a temperature of 55 decreasing to, let's say, 50 probably, or 51, or even 49 for that matter. This is the value that should have existed at this point, but he is mentioning 35, which could have been, according to our understanding, as I said, that the student may have misread the value. It could have been 53 actually, which he written down as 35 due to experimentation stress or due to fatigue, right? So this value appears to be biased. It appears to be wrong, right? But 52 after 35 looks like that it is following the trend. Now, as we're conducting the experiment, it is a good idea to check that this value doesn't fall into the trend. So should I repeat the experiment? Should I reconsider, or should I just reject it? So if you've done the experiment, a good idea would be to repeat the experiment, do exactly the same thing, but it's highly unlikely that you will get the same values again. So what the solution would be to reject this value, to save time. That's all, right? Okay. So we have to mention where the anomalous reading is. So we mentioned the exact point. At time t 150 seconds, the reading of temperature came out as 35 degrees centigrade, which we think is an anomalous point. So we mentioned why is that so. So the reading does not follow the trend as mentioned earlier. It is much smaller than the previous reading. It should have been close to 50, 53, 51, or it could be any value, it could be any other value, right? Or for the sake of discussion, let's say it should have been between 55 and 52. We can expect that these two values are accurate according to the trend. So the value should be somewhere in the middle. Could be 54, could be 53, could be 52, right? So as it's not that value, so we have identified this point as an anomalous point. Use the temperature reading in table. Now always pay attention to the instruction of the examiner. He's asking you to take the values from table 2.1 to calculate the decrease in hot water temperature after 180 seconds. So the last coordinate, we have to measure the delta T. So the experiment starts at 73, finishes at 34. This starts at 75, finishes at 52. So pick out these values. The first one is for the cold water and the second one is for the warm water. It's a good idea to write this down so that you don't misrepresent or misplace the value. So this will be 39 simply, and this will be 23. Then he says comment about these answers. So he says use your answer in D2. Whatever answers you've mentioned in D2, this is your D2. If you note, this is D and this is part 2. So whatever you found over here, use these answers to justify a statement that the examiner is going to ask you. He says, how does it affect, right? So how the temperature of the water on the outside affects the cooling of the hot water in the test tube. So conclusion should be very straightforward by, again, using the values from the table and using the values from at least the previous part, that the cooling is faster in cold water from, again, picking a coordinate, that's up to you. Or you can just use these values that over a course of 180 seconds, the cold water caused a temperature difference of 39 degrees and the warm water caused a drop of 23 degrees. So the cooling effect in cold water was faster. Or you can use a simple coordinate from this table, right? I have selected a time frame from, for the sake of discussion, from 30 to 60. So we mentioned that from 30 to 60, it dropped from 54 to 45, and this dropped from 68 to 63. This is a difference of 9 degrees, and this is probably a difference of 5 degrees centigrade, right? So this is what we're discussing in the answer. A temperature decreased by 9 degrees, while in the warm water, the same time frame, it decreases by 5 degrees. So again, air cooling is faster in cold water. Conclusion was first, and then we mentioned why is that so. Now suggest one improvement to the experiment procedure described in A and B that allows for more valid comparison for the rate of cooling. Again, this is a common question for cooling effect or for the cooling apparatus in questions, that it should have same initial temperature and same volume of water used in the measuring cylinder, owing to the heat capacity, because of course it's about the energy content. So the mass or the volume of water should be the same. If the mass is high, then there will be more energy in it and it will require more time to cool down. That's why we want to make sure that volume should be same. Question number 3 is again a repeated question from the chapter of moments and principle of moments. He says that they want to balance the meter rule with a fixed mass m at the 5 centimeter mark. And if this is 0, this is fine. Okay, fine. The student then pivots at 50 centimeter mark, which is understandable because of the uniform. If it's a uniform rod, it will be balanced at 50 centimeter mark. Place another load of mass 50. Now, this 50 grams is a known mass, right? One of them, this is 50 grams, this is known, and this is capital M, which is not known. He says that until the ruler is close to balanced as possible. Okay, fine. Which means that the clockwise movement is equal to the anti-clockwise movement. Now he mentions in the next part, he says, take the readings from the ruler and use them to determine the position of the center of the mass of the 50. Now, first notice that the center of mass is at this point, right? If you were looking at it from the side, this is where the center of mass exists. Now, the first reading that is visible to you comes from this location, which is this reading. If you look very closely and always use a ruler for this, what I recommend to the students is use a ruler and draw a line with a lead pencil, and it will make your life a bit easier, right? So the first reading over here is 93.5, which is evident at this location. The second reading at this point, although looks like 96, but then again, as I mentioned, place a ruler, always place a ruler over here. So we find it as 95.9. So this reading is 95.9, and we know that the center of mass of a uniform object exists at its center. So first we take the difference of these two readings by subtracting 95.9 from 93.5. When you subtract them, you get 2.4, which means that the total diameter of this mass is actually 2.4 centimeters. And we know the center of mass will be, from this side at least, will be 1.2 centimeters, half of it. So 2.4 divided by 2 gives us the center of mass. Where should it be located? It is at 1.2. Now he asks us that determine the position of the center of the mass from the center mass on the ruler, right? So then, since we know that this is actually 1.2 centimeters above it or more than it or after 93.5, that is why we are adding 93.5 with 1.2 to get 94.7. So exactly at 94.7 centimeter, this mass, center of mass, exists, right? This will be utilized probably in the next question for the calculation of moments. So 94.7, write down 94.7 centimeter over here. Then he says calculate the distance d from the center of 50 grams from the 50 centimeter mark. You see, now he's asking you to calculate this d, which starts from 50 and ends at 94.7. So that will be very simple. 94.7 minus 50 gives us 44.7, which means that this actual length, absolute length, would be 44.7 centimeters. So this is 44.7 from the pivot. Then he says calculate the value of 1000 by d. So d in the previous part is 44.7. Full calculated value from the calculator is going to come out like this. But since you're dividing with a 3 significant figure number, your answer should also be 3 significant figure or up to 3 significant figure. If you're still confused about it, go forward, go beyond this page and see what the values in the table are being represented as. We can see that the whole table represents 3 significant figures. So it's very pertinent to accept this value as 3 significant figure as well. Then it is difficult to balance the rule exactly. Yes, we understand that. Describe a technique the student uses, how he has balanced this, how he makes sure that it is balanced. Again, you have to make a general comment that find the balance point by moving the mass so that the rod moves. First, it moves clockwise, then it moves anti-clockwise, and the center of those two extremes would give us the exact location where it will be balanced. So what he's trying to say is that sometimes, or first try to move it closer to cause an anti-clockwise movement, then move it away to cause a clockwise movement, and keep moving it back and forth, keep doing it until you find a point where this is perfectly flat. Right? It's a hit and trial method. Okay, he says the student repeats the reading for 1600 grams and records the value. Okay, fine. These are the values. Then he says that provided on figure 3.3 on page 13, plot a graph of m against y-axis. So the first thing you should do is label the axis. Y-axis labeled with m/grams and against d on the x-axis, which is 1000 over d. So then label this over here. 1 over 1000 as 1 over 1 centimeter with its unit in place. Then what I recommend to the students is generally write down which each of the column is going to be represented on what axis. That's a good idea generally, because then your eyes, or at least your concentration, won't be focused on this table. I usually write down which one is y-axis and which one is x-axis so that I can quickly pick out the coordinates and plot them on the graph and save time. So again, your technique might be different, but now we have to understand. He says, draw the line of best fit. And the good thing about this question is that he said, do not need to start from origin. You can, but you don't have to. So now we have to make sure what scale we are going to use. So the values start from 50 and end at 100. I have approximately 12 spaces over here on the y-axis, if I look at closely. So this starts from 1, 2, and so on up to 12 places at this location. It's always a good idea to start, not to start from exactly the first coordinate, start from something that has a margin. So over here, I'm starting from 45. I'm giving a gap of 5. Again, it is by hit and trial. Although you can do it this way as well, that from 50 to 100, there's a difference of 50, and you have 12 boxes. When you do that, your answer comes out as 50 divided by 12 comes out as 4.16. 4.16. This can't be the scale for this graph. So we have to round it off to a multiple of 2 or 5. So this comes down as 5. So what you selected from your mental calculation is approximately right. So a gap of 5 gives us the final value as 105, which is much greater, which is way beyond 100. So we have some head space over here. And we also have some head space over here as well, right? So perfectly balanced on both sides. Then again, since we are not required to start from the origin, we can go back to making decision for the x-axis. It starts from 22.4, ends at 45. So a good starting point should be 20, right? Or 15 for that matter. So we are starting from 15, right? Again, some headspace on the left side. And then we're finishing at 48, 45 over here, somewhere along this line, right? So again, on this axis as well, we can find that a gap of 5 was sufficient. You can calculate the same way we've done this for y-axis. It's your choice. You can start from 20 as well. It does not matter. But I wanted some head space over here as well to see if there was going to be a y-intercept or not. Although y-intercept I calculated using y equals to mx plus c by picking any coordinate and putting it into y and x before, in the first step, you'll find the gradient and then you'll find the y-intercept. We generally avoid the y-intercept finding it from, let's say, the line itself, right? Okay. So now, since you've plotted all the, you've made the scale, now you're going to pick up the coordinates. You're going to pick the coordinates at 50 and 22.4. So I'm just going to show you one of them. So we have one coordinate at 50 at 22.4, right? Similarly, all the coordinates will be plotted like this. Once you've done that by drawing crosses, you will draw the line of best fit through all those points. I've done this over here. Let me zoom out and show you what that line may look like. Although this is a very thick line, you should be using a very thin lead pencil for this. Now notice that these 3 points, point number 1, 2, and 3 are exactly on the line. This one is slightly below, but we can accept it to be on the line. But when we go to the upper side, we see that one of the coordinates is at the lower side of the line and one of them is on the upper side of the line. So we have perfectly balanced the undercompensation of this coordinate and overcompensation of this coordinate because we're passing from exactly the center. So our line of best fit is accepting or is including the trend of this coordinate and also compensating for the trend of this coordinate. It's taking care of both coordinates at the same time. Although not exactly the coordinates themselves, but that is what the line of best fit is supposed to be. Then in the next part, he suggests that you're supposed to find out the gradient. Once you've drawn the line of best fit, please draw the gradient. Now for the gradient, you're supposed to mention 2 coordinates and you're also supposed to mention this on the graph itself. So always show the examiner how and where you've picked the coordinates from. So let's see that I've picked a coordinate from 25 and 55. So let's say at the line of best fit, we have 25 and 55. So this is approximate. Again, you are supposed to count the boxes and do this more accurately. I've done this roughly, right? So one of the coordinates exists at this point. I'm making a large blob at this point. These dotted lines are not required. And even so, this blob shouldn't exist. It should be just a small coordinate over here on the line itself, right? Then the second coordinate that we've picked is 42, 95. So from 95, from 95, we can see that the coordinate exists somewhere at this location, and probably it will be at 42, right? Okay. So now, once you've drawn these coordinates, what are you supposed to do? Please draw a triangle for the gradient like this. If these are your 2 coordinates, then place a ruler, draw a dotted line like this, and then draw a dotted line like this with the ruler and a lead pencil to show the examiner that you're taking this part of the line for calculating the gradient. Ideally speaking, anything that covers more than 50% of the line, you see, this is the length of the line. So he mentions that the coordinates taken should be at least greater than 50% of the line. So we can see that the line that we've selected from this point up to this point is more than 50% of the line itself. So we are in the safe zone. Although I would recommend that if you can choose even further points, let's say this one, this will be even better. Puts you in the safe zone, right? The examiner cannot deduct marks or not choosing the right length of the gradient. Okay, so once you've done that, we can put in these values in this formula, which is y2 minus y1. We're familiar with that, and x2 minus x1. We get this as the full answer, but up to two significant figures, we can write down our answer. This is 2.4. And questions like this always have a range. So in the marking scheme, we mentioned that the answer can be from 2.0 to 2.4 inclusive. Inclusive means that 2.0 and 2.4 are included in the answers. They are not excluded, right? So our answer is approximately correct. Then he says, calculate the mass of this answer by multiplying it with this 2g. Okay. So we have 22.2 multiplied by the gradient, which is 2.4. Comes out as, now you have to show the calculation as well. This is 53.28, my answer is, by calculating 22.2 multiplied by 2.4, which is the gradient g. So I will write down 53.4 up to three significant figures. Okay. All right. So then he says, suggest why this method of determining the mass m of the fixed mass is unsuitable if the moving load is greater than 40. You see, if we go to the table as well, right, and if we look at the line of the gradient, right, so below 40, we can see that the results of this 1 over 1000, or the value of d itself, will become too large, right? The value of d will become too big, which means that we are going to exceed the length of this even more. You see, at 40 grams, let's say, the distance comes out as a certain length. If you reduce it even further, the total moment decreases and the mass should be at a distance from the pivot, which is approximately not located on the ruler itself. It will exceed the length of the ruler. This is a common question again. Why can't we do this? Right? So it would not be possible as the d increases beyond the available length of the rod. Right? So it's a physical limitation. Okay, question number 4. This is a new addition in the syllabus from the Cambridge examiner. It says a student wants to investigate the focal length, or wants to find the focal length. This is the formula that he uses, and there are variables of u and v. He just mentions in theory what u is and what v is. He wants you to figure out from the statement where they're going to be located. So we can see the u is distance between the object and the lens. So the object itself is the lamp. Lamp produces the object's shadow, right? So u should be over here, and v will be somewhere along this line, and v is the distance between the focused image of and the lens. So this is the lens, and this is where the cardboard may exist, where the screen may exist, right? Where you want the image to be formed. So then he says the lamp is connected to the power supply and the experiment is carried out. He says, in your experiment, in your plan, in your explanation, list out these following things at least. Now the question is for 6 marks. There are 5 points. If you take care of these 5 points to the best of your knowledge, you still get 5 marks out of 6 as a bare minimum. So please, when you've written down your theoretical part, always come back to this list and check out the points that you've already mentioned, right? Then we can look at how to get the 1 extra mark. Now let's see. He says list any additional apparatus that may be needed. You may not have to make a list. You just have to write this down in a theoretical statement. Draw the apparatus image again. So what I generally suggest to the students is pick out this diagram, draw it again, and just mention where the u and v are going to be. Where u and v are going to be, right? So then we have the third part is explain briefly how to do the experiment. Let's look at that, and then state the steps taken to obtain a sharp focused image. We will talk about that as well. Explain how to use the readings to determine f. Again, for f, he has mentioned a formula, right? But we need to measure u and v to figure out what the value of f is going to be. Okay, all right. So first we see use a meter rule to measure the value of u and v. That's what we're supposed to do, but we mention meter rule for its calculation, for its measurement. And the image of the bulb will be formed on the piece of cardboard that you're going to place at this location, right? So making a cardboard is necessary. Label the cardboard that this is our place where the image or the sharp location of the image will be formed. So that is also necessary. And then the distance v is also mentioned, okay? Then how to obtain the sharp image. So move the lens and the screen to obtain the sharp image. So basically what we do is we move the position of the lens forward and backward. We move the position of the cardboard forward and backward. Sometimes the position of the card or the lamp itself until a sharp image is obtained. And when we do, we measure the value of U and V at those locations. So once you've done that, we will conduct the experiment, and this is again an improvement, a suggestion over the standard procedure, because he's not asked us about the improvement, but we will still mention it for an extra credit to get 6 out of 6. So conduct the experiment in a dark room. So all the experiments for a lens calculation, for a lens measurement, are generally conducted in a dark room to avoid with the external light interfering with the experiment. The last point is repeat the experiment and record 6 different readings for the sets of U, and then find the average of those values and calculate F for the final answer. Now, why do we need 6 values? This is a common practice that if you want to draw a straight line, if you want to draw a line of best fit, or if you want to use the graph for the calculation of the focal point, then it's a common practice to use at least 6 readings for the graph. You will go back and see that even in the question of the examiner or given by the examiner, there are at least 6 readings to go about. So 1, 2, 3, 4, 5, and 6. Similarly, if you go back to the next question, the previous one of the cooling water, you will see that there are 1, 2, 3, 4, 5, 6, 7 readings for this current experiment, right? So it's always going to be 6 or more than 6. It's a scientific experiment, scientific practice. We need 6 readings, or we will take 6 readings for the graph purpose. So mentioning this point always puts you at a great advantage in terms of your reputation, in terms of your knowledge, in terms of the examination attempt. That is all.